Welcome. This is the lecture for Chapter 5, Choice. Now this is the chapter where we sort of bring things together. We know that a person's choices are limited by their budget. We also know that people have preferences. If we understand what people can have from their budget, and we understand what people want to have from their preferences, if we combine these two, we can figure out what people will choose. Of the things that they can have, they'll pick the one that makes them happiest, that gives them the most utility. Okay, here is the budget constraint, a budget constraint. Pretty simple. And here it is superimposed over an indifference, set of indifference curves. Now, for these 2 points, laser pointer, this one and this one, both are on the budget constraint. So both are affordable, but just barely. This person is spending all of their money, which is what we know they will do in this model. So which one will they pick? Well, they'll pick the one that gives them the most utility, that puts them on the highest indifference curve. These are all the consumption bundles that a person can have. They're in the budget set. These out here are beyond the budget constraint. They're outside the budget set. So the person cannot have, for example, that bundle right there. So we know that the person will choose something in there, up to and including the budget constraint line. Of all of those choices, which one makes the person happiest? Well, points that are to the northeast, consumption bundles to the northeast, make the person happier. So we see here the things a person can afford to the upper right are things that make the person happier. So this person is going to pick the one and only consumption bundle of the ones that they can afford that gets them to the very highest indifference curve. You can see here that this one doesn't do that. It puts them on this indifference curve. But they can afford a bundle on that indifference curve. Since this curve is higher than that one, they prefer that bundle over that one. Geometrically, hopefully, you can see that the choice the person will make, the bundle that they can afford that will make them happier than any other, is the one where the indifference curve is exactly tangent to the budget constraint. So if you know someone's budget and you know their preferences, you can calculate this point. All you have to do is find the point where the slope of the budget constraint is exactly the same as the slope of an indifference curve. This is arguably the most important graphic image in the entire textbook. This is the core of consumer theory. Consumers have preferences. They also have budget constraints. They pick the combination of X1 and X2, apples and oranges, whatever, that maximizes their utility given their budget constraint. So this is the one and only bundle that will make them happier than any other that they can afford. In an introductory course, demand is generally just a function of the price of a good. Prices of other goods, income, don't matter. They're ignored. Here, we take those things into consideration. So, the most preferred bundle that's affordable is called ordinary demand. And it will be denoted by X1 star and X2 star. The star in this case means the optimal choice quantity of X1 and the optimal choice quantity of X2. Okay, now, we have to set a couple of limits on, not in the mathematical sense, but a couple of limits on consumers' choices here. Otherwise, we'll get odd results. We're going to consider first the case only where the consumer buys a positive quantity of both X1 and X2. The consumer is not spending all their money on X1 and nothing on X2, or the other way around. This gives us an interior solution. I'll show you why it's called interior later. Okay. Here, an interior solution in this simple example means that they're not at that point and not at that point. They're somewhere in between. Okay. Now for well-behaved preferences, and we've defined those earlier, we know that this preferred bundle has to satisfy two conditions. We know that the budget will be completely exhausted. The person will spend all of their money. And we know that the slope of the budget constraint, which is the negative of the price ratio, and the slope of the indifference curve that contains that optimum bundle will be the same. The slopes will be the same because it's a tangent point. How do you find this information? Well, what do we know about the optimum affordable consumption bundle? We know a couple of things. One, we know that at that point, the slope of the indifference curve, we know it's a tangent point, the slope of the indifference curve will be equal to the slope of the budget constraint. Well, what is the slope of the indifference curve? That's the marginal rate of substitution. The slope of the indifference curve, the marginal rate of substitution, is the rate at which you are willing to trade off apples for oranges. What is the slope of the budget constraint? Well, it's negative the price ratio. That's the ratio at which you can exchange apples and oranges. Well, we know at the optimum consumption bundle, the slopes are going to be the same. So we know the consumer will choose a bundle where the rate at which they're willing to exchange apples and oranges is exactly the same as the rate at which they can exchange apples and oranges. The marginal rate of substitution will equal the price ratio. We know one other thing. We know that whatever bundle this person chooses, they will exhaust their budget. They're going to spend all of their money because we've defined it such that the person only gets utility from X1 and X2, apples and oranges, not from money itself. So now we just have to find these things. The marginal rate of substitution here. How do you find that? Well, what is it? Let's look at an example with Cobb-Douglas preferences, meaning that for two commodities, this person's preferences take this form. Utility is equal to the quantity of X1 the person has raised to some power A times the quantity of X2 they have raised to some exponent B. The marginal rate of substitution is equal to the negative ratio of the marginal utilities. So we have to find the marginal utilities for these preferences. The marginal utility for commodity 1, how much utility this person gets from one more small unit of X1. Well, it's the partial derivative of the utility function with respect to X1. That becomes that. And the utility a person gets with these preferences from one more small quantity of X2 is the derivative, the partial derivative of the utility function with respect to X2. So that is the marginal utility of commodity 1, and that is the marginal utility of quantity 2. There we go. Okay, let me show this example to you. Assuming I can see it because the font is very small. The partial, and there we go. The partial derivative of u, so du dx with respect to x1 remember, for partial derivative, you just treat everything that's not the variable you're interested in as a constant. Because remember from single variable calculus, a derivative, in a sense, is just the slope of the curve. When you're dealing with only one variable, well, there's no question about the direction you're dealing with. It's just the slope. There's only one of them. But when you're dealing with a multivariable function, imagine it as a surface in multiple dimensions. At a given point, if you say, well, what's a slope right there? You have to ask, well, slope in which direction? If you want to know the slope in the A direction, then you have to hold B constant. Treat it like a constant, makes it easy to take the derivative. So let's show that here. X1 to the A power, X2 to the B power. Just to make the math a little more obvious, I'm going to reverse the order, but you know that doesn't change anything. So that gives us X2 to the B power times X1 to the A power. We want to know the slope in the X1 direction, the partial derivative with respect to X1. So anything that's not X1, it's a constant. That's a constant. So what is the derivative of some constant times x to the A power? It's, well, that constant. Now for x to the A power, we bring the A down, so it'd be A, and then x1 to the A minus 1. And that's the same as you have there, although it's reversed. And you do the same thing to take the derivative with respect to x2, the partial derivative. For some of you, this will be old hat, but it never hurts to see an example. There we go. Now I'm going to take the partial with respect to x2. So now x1 to the A power, treat it just like a constant. The derivative is equal to b times x2 to the b minus 1 times this constant, which is what you have there. Partial derivatives really are not that hard. And boy, are they useful in econ. Okay. We know, if I can make this work, here we go, that this consumer will choose a bundle where the marginal rate of substitution is equal to the indifference curve. Well, we now have found the marginal utility of x1 and the marginal utility of x2. Put them in a ratio with a negative sign out front. That is the formula for the marginal rate of substitution. Well, just plug in what we found, which is there. Do a little simplification, and you get that. So, we know that at the optimum bundle, the marginal rate of substitution, which is there, will equal the price ratio. Do a little algebra to make it simple. You can drop the negatives because they cancel, and you get this. We know that at the bundle the person will choose, the optimum bundle, the optimal quantity of x2, the optimal quantity of x1, they will have this ratio. Okay, we're done. Almost. There's still one problem. We know that at the optimal consumption bundle, there we go. Just chopping off the top of my head. We know that at the optimal consumption bundle, the budget constraint, the budget line, will be will have the same slope as the indifference curve. But that also happens at points inside the budget constraint, in the budget set that are more than affordable. This condition would be satisfied at bundles where the person does not spend all their money. Let's see if I can draw you a really quick example. This is the quantity of X1. I can draw. This is the quantity of X2. Here's a budget constraint. And there's an indifference curve. Let's just assume that those touch because I draw badly. Okay. Now we know visually that's the consumption bundle the person will choose. And we can see, making allowances for me being a terrible artist, that at that point, the budget constraint and the indifference curve have the same slope. But here's another indifference curve, which I will draw equally badly. At this point right here, this consumption bundle, the slope of the indifference curve is equal to the slope of the budget constraint. This condition over here is satisfied. But this bundle is not the one the person's going to choose because they could get this one where they have more X1 and more X2, and they can afford it. So we need to add a second constraint, that the person will spend all of their money, which would eliminate that possibility. So we know that for the bundle we're looking for, the marginal rate of substitution will equal the price ratio. We also know that this will be true. The person will spend all their money. So we know this is true. If I can make my pen work. Whoop. Maybe I can't make my pen work. Okay. I believe you can see the cursor. We know that this will be true. The rate at which a person can exchange X1 and X2 will be exactly equal to the rate at which they're willing to exchange it will be the same as the rate at which they can exchange it. We also know that they'll spend all their money. Well, we know both of these equations will be true at the optimum consumption bundle, so we have two equations and two unknowns. Early on in high school, maybe junior high, you learned how to solve these. This is why we did a little algebra to get one of the x's on one side here. Makes it easy to substitute in. So substitute in, and we get P1x1 plus P2 times this bit from here. Simplify it down, you get that. Substitute back into one of the equations. The budget constraint's easy, and you get this. So we've now figured out that the most preferred affordable bundle for a person who has Cobb-Douglas preferences, this form, will be that. If you know what A and B are, because you have to know the person's preferences, you know their income, M, and you know the prices. You can just plug them in and calculate. At the optimum bundle, the person will purchase this many of X1 and that many of X2. Here it is graphically with the math. Pretty well, I was going to say pretty straightforward. Then again, I've been studying this for a lot of years. I know this takes some getting used to for people who are new to this. Okay. Now, Remember, up front, I said that this only works if we constrain the person's choices a little bit. Their preferences have to be well behaved, and they have to consume non-zero quantities of both x1 and x2. Pardon me. So here we begin to look at why we have to put those extra limits on it. If these things are true, then we know that the person's spending will equal their income. Here it's y rather than m. And this will also be true. But what if the person doesn't obey those extra constraints that we put on? In particular, what happens if they buy zero of one or the other? Remember, I said that having a non-zero quantity of both items as the optimum choice, we call that an interior solution. Well, if they do buy none of one or none of the other, we call that a corner solution because it looks this way. Here, assume that x1 and x2 are perfect substitutes for this person. And just to make it easy, assume that they're willing to exchange them at a one-for-one rate. So the marginal rate of substitution is -1. Now here, you may look at that and think, budget constraint. No, these are not budget constraints. These are indifference curves. This is that special kind of indifference curve where people are always willing to trade apples and oranges at a particular rate. How many apples they have, how many oranges they have, make no difference. Here, they're always willing to trade one apple for one orange. Could be at a rate of 2 to 1. The key is that the ratio they're willing to trade them off is a constant for all quantities of either. This red line is the budget constraint. Now, if we assume, just a simple example, the marginal rate of substitution is, in absolute value terms, 1. This person is willing to trade, let's say x1 is apples, x2 is oranges. This person's willing to trade one apple for one orange, no matter what. So the difference curves are straight lines, and these are perfect substitutes. But the rate at which the person can exchange apples and oranges is not 1 for 1. It's this line. In this example, if a person spends all their money on x1 apples, they'll have this many. If they spend all oranges, they'll have that many, more. Well, that means that here, apples are more expensive than oranges because the curve comes in. Let's see if I can make that work. There we go. That's a little easier. So if you spend all your money on apples, you only get that many. Spend all your money on oranges, you get more. So we know at the optimum bundle, this person, the ratio at which they're willing to exchange apples and oranges will be exactly the same as the rate at which they can exchange apples and oranges. The slope of the indifference curve, like that one, will be the same as the slope of the budget constraint. It's pretty obvious. No such point exists. So what will this person do? Well, they're going to pick this bundle here. They're going to spend all their money on oranges and none on apples. Think of it this way. Let's assume the person was here at this bundle. Let's just call it 10 apples, 10 oranges. Well, this person can trade one apple and get 2 oranges. If they did that, they'd go left 1 and up 2 to, for example, this point. Well, now they're on a higher indifference curve, one in between these two that are shown. And they can do it again. They can keep trading away apples and getting more than 1 orange for each one. They're indifferent at a rate of 1 to 1. So every time they do this, they're better off. So they'll keep moving left until they get there. Now at that point, this person actually would be willing to do it again. This person believes 1 apple and 1 orange may give them equal happiness. They're indifferent. But by giving up 1 apple, they can get more than 1 orange. They'll be happier by doing it more. The only reason why this person will not continue trading them off is because, well, at this point, they're consuming 0 apples. They don't have any left to trade. This person cannot consume negative some number of apples. And so they're stuck at the corner. Thus, corner solution. And here it is again. This person will consume at the optimum 0 x1, and they'll spend all their money on x2. They'll be able to buy whatever their income is divided by the price of x2. So this will be the optimum consumption bundle, even though the slope of the indifference curve is not the same as the slope of the budget constraint, because it's a corner solution. And if the prices were different, they might end up here with 0 of x2, purchasing no oranges and spending all their money on apples, depending on the relative prices. So, well, that's pretty much what I just said. Here, this is the utility function for perfect substitutes, a utility function for perfect substitutes. And what's more, where you're willing to trade them off at a ratio of 1 to 1. This could be 2x1 plus 1x2, and they'd still be perfect substitutes. So in this simple case, this is the utility function, where the person is willing to trade off at a rate of 1 to 1. Well, then they're just going to spend all their money on whichever one is cheaper. Now here's another interesting case. What do you see here? Do you see a budget constraint? Probably. The thing is, there's also an indifference curve here. Only one of them. But the reason why you don't see it is because imagine it's being underneath this green line. If the budget constraint, let's see if I can do this, is that, wow, I'm bad at this. If that's the budget constraint, and that horribly drawn thing is an indifference curve, imagine they're one on top of each other, then there we go. Then all of these points on the green line are affordable, but just barely. Inside here, that's the budget set. This is the budget constraint. So this person will buy something on this green line, some combination of x1 and x2 on the green line. But they're all on the same indifference curve. So which one will this person buy? The answer is, I don't know. And this person, what even more, doesn't care. The person can spend all their money on x2, and they'd be here, all their money on x1, and they'd be here, buy some of each, any combination on the green line, and they'll be exactly equally happy. This person doesn't care. All of these consumption bundles are the same indifference curve, give the person the same utility. This person will flip a coin. Here's another example of preferences that are not well behaved. These are preferences that are non-convex, but what does that mean? What's the real world interpretation? Imagine that the indifference curves went that way. Just ignore the black ones for the moment. This is a convex preference. So if the person had a whole lot of x1 and very little x2, or the other way around, well, they could trade them off to get some intermediate amount, because we know the budget constraint's a straight line. We know it goes through those 2 points, therefore it has to go through that point. An intermediate amount, a more even mixture, would make the person happier, because instead of being on this indifference curve, they'd be up on that one. But that's for convex preferences. Here, the preferences are not convex. Imagine a person, well, actually have it on this one. This is a budget constraint. This person can spend all their money on X1 and have that many, or they can spend all their money on X2 and have that many. They can also spend all their money on any combination in between. What happens if this person chooses a mixture, not all X1 or all X2? Well, then they'd be, for example, there. But that's a lower indifference curve, isn't it? These are all affordable. Which one gives the highest utility? This one certainly does not. It's on this low indifference curve. This one does not. It's on that indifference curve. It's this one that gives the most utility. It is the bundle that is just barely affordable and gets the person to the highest indifference curve. When you have non-convex preferences, you're frequently going to end up with a corner solution. This person with these preferences will never choose an intermediate amount, will never choose an interior solution in here. They will always choose a consumption bundle at one of the corners, like that one. But here, notice something else, that the tangency solution, the consumption bundle, where the slope of the budget constraint equals the slope of the indifference curve. In other words, where the price ratio is equal to the marginal rate of substitution. That gives you that point. It gives you the wrong answer. So this procedure only works if preferences are well behaved. Here's another case where it doesn't work right. Perfect complements. The textbook calls these kinky solutions, meaning there's a kink in the indifference curve. With perfect complements, here's a simple example. This person gets utility from consuming these things in a fixed ratio, A. So this is like right shoes and left shoes. In that case, A would be 1. What is the marginal rate of substitution? What is the slope of the indifference curve? I have tremendous respect for Halvarian, but that's the symbol for yen, as far as I know. Then again, I'm probably the one wrong. What is the slope of the indifference curve on that vertical segment? Well, the slope of a vertical line is not defined, so it doesn't have a slope. The slope on this segment is 0. That's defined. Well, just visually, if this is the budget constraint, you can tell what this person's going to choose. They will choose that consumption bundle right there. It gets them on the highest indifference curve, namely that one. But the tangency condition doesn't hold, because what is the slope of the indifference curve at that corner bit, at the kink? It's not defined mathematically. Visually, it still works. Mathematically, it won't, because at that point, the indifference curve slope is undefined. So this person will consume this quantity. We know that's true, and we know that's true because these are perfect complements. So just substitute one in the other. That's what the person will consume. And there it is shown graphically with the math. The cases of perfect complements and perfect substitutes, they're good for teaching purposes. But remember, those perfect cases don't exist in the real world. Some things are very close to perfect complements, very close to perfect substitutes. But in the real world, and when you get a little more advanced into this, you are going to see corner solutions. There'll be corner solutions for a variety of other reasons, but just not. So it's important you understand those can exist, where the optimal consumption bundle does not meet the tangency condition. But it will be because preferences are wonky in some other way, which we'll get to. Okay, thank you very much for watching. I will see you next time.